All right, we're going to jump into properties for multiplying terms with exponents. The first thing we want to do is define a couple of terms. The first is going to be what a monomial is. A monomial is basically a number, a variable, or a product of a number and a variable with non-negative integers. And secondly, we have this thing called a constant. And what a constant is it's just a monomial that's a real number. So, for instance, we have a monomial in the left-hand column listed. Notice here are multiplications of positive variables with positive exponents. This -7 is our constant. The constant does not have to be positive. The exponents, however, do. We have 5x squared. There's your constant of 5, positive exponent. In this case, we have positive exponents, 1 and 3, with a positive coefficient or positive constant in front. Notice that in this case, the coefficient in front of this term is a 1/12. We have 5/8 here, all variables of positive exponents in this case. Notice these are examples of terms that are not monomials. This is not a monomial because I have a -5 as my exponent. This is not a monomial because I have a variable in the denominator. This is not a monomial because there are two terms linked by addition, and it clearly states in our definition that we have to have a product of a number and one or more variables, not a sum. So let's go through. In this term, 5 is a constant in this case. It's also called a coefficient. X we call the base, and 9 is our exponent. Sometimes people will call them powers. Now here's an example of a true statement that we know about. We have 4 times 8 equals 32, no big deal. I'm going to convert all these to powers. So we have 4 is equal to 2 squared, 8 is equal to 2 to the third, and 32 is equal to 2 to the fifth. And I want to look at the relationship between these two terms multiplied together and their actual product. And we notice that if we take and keep the base the same and add the two powers, we end up with our 32. So in general, we create a rule from that. When multiplying terms with equal bases, you want to keep the base the same, and then you want to take and add the powers. So if I have x to the a times x to the b, x is our same base. We add the two powers and keep the base the same. So I have a few examples here. 6 to the 7th times 6 to the 3rd is going to be keeping the base the same, 6, add the two powers, 7 plus 3, or 6 to the 10th. Likewise, in this case, my base is the same, so I keep the base and add the two powers, and I get x to the 17th. In this case, notice we have two monomial terms. We're going to match up these terms such that the same bases get compared and the powers get added on those same bases, and then that's going to be multiplied by the product of bases of b, and I'm going to add those powers. So I have a to the 11th, b to the 14th. Now, in this case, since I don't have the same base, these terms cannot be simplified. So this is still 2 to the 3rd times 3 squared. In other words, 8 times 9, which is 72. But there's no fancy combination of this. This is not equal to, notice, not equal to 6 to the 5th. Okay, so don't ever try to do that. Have to have the same base. So here are some more practice problems. I have three terms in this case, all with the same base. So I keep that base, add the exponents, and you'll notice I have 6 to the 7th. In this case, notice the multiplication dot is not there. I just have parentheses around terms, which means multiplying. And also notice in this case, my same base is x. I have a constant of 3 and a constant of -2. I can multiply those terms together because they aren't base terms with exponents. So 3 times -2 is -6. Then I keep the base of x the same and add the two powers, which is going to be -6 x to the 12th. Likewise, in this case, I multiply my constant terms together of 5, 6, and 3. That's 30 times 3 or 90. And then I have w's comparing, so that's w to the 5 plus 3. Y has no common base other than that y to the 4th term, so that just stays in the problem. I therefore get 90, w to the 8th, y to the 4th. Finally, we have this situation. Here's a, b. I take and add the exponents. So I have a to the -3rd, because 6 plus -9 is -3, and b to the 17th. Later, we'll find out what goes on with these negative exponents. That's clearly not a monomial because that exponent is negative, but it is a solution. We typically don't leave negative exponents in the answer, but for now we will. Let's look at another true statement. I have a situation here where I have 2 to the 3rd, and I'm going to square that. Now, if I square anything, that means multiply by itself. So if I take 2 to the 3rd times 2 to the 3rd, keep the base the same, add the powers, and I get 2 to the 6th. Likewise, if I have 5 squared raised to the 4th, I have something multiplied by itself 4 times, same base, add the powers, and I get 5 to the 8th. Notice the relationship between the powers and the final answer in both cases. In each of these cases, I've kept the base the same and I've multiplied the powers. So the general rule is when raising a base with a power to a power, we keep the base the same and multiply powers. In other words, if I have x to the a raised to the b, that's the same base, x, the a times b. So again, let's go through and practice some problems. In this case, you'll notice that I have bases with powers raised to a power, so I'm going to take and multiply those powers. So this is same base, 4 times 5 power, same base, 3 times 5 power, or x to the 20th and y to the 15th. Now in this case, this 2 does not have a power associated with it, but it's an unwritten 1. So this is really base of 2 to the 1 times 3 power, x to the 3 times 3, and w to the 7 times 3. 2 to the 3rd is going to be 8, x to the 9th, w to the 21st. Moving forward with our next example. Once again, unwritten exponent on the 3, that's going to be a 1, so this is 3 to the 3rd, a to the 6th, c to the 12th after multiplying. This term is going to be multiplied by a to the 42nd and c to the -6th after multiplying once again. Now you'll notice we have another step. I have to take and multiply these two terms together, which has a different rule. First of all, 3 to the 3rd is 27. And then I have common bases of a. So since I'm multiplying now, I keep the base the same and add the powers. And likewise with the base of c, I add those powers, thus giving me 27, a to the 48th, c to the 6th. Now you'll notice the terms are moved all over the place in this case. I have 4 outside of everything, so there's no powers associated with that 4. So this is just 4 times, I have bases with powers raised to a power, so I'm going to multiply powers in this first step. X to the 6th, y to the 14th. Now in this case, unwritten power of 1 on both the 2 and the x. So this is 2 to the 4th, x to the 4th, and y to the 12th. And now we're reduced to a multiplying problem. Let's simplify real quick. This is 4 times x to the 6th, y to the 14th. 2 to the 4th is 16, x to the 4th, y to the 12th. Now we're going to take and multiply everything across. Since the 4 and the 16 don't have any bases with powers associated, I multiplied those two together. 4 times 16 is 64. That's x to the 6 plus 4 power, and y to the 14 plus 12 power gives me 64, x to the 10th, and y to the 26th. Couple more. Now we're going to take and put almost everything together in this case. Notice unwritten power of 1, unwritten power of 1 here. This is 5 to the 3rd, p to the 6th, q to the 12th, plus, and this is an unwritten negative 1. Negative 1 to the 6th power, p to the 6th, q to the 12th. So I'm going to simplify a little bit. This is 125, 5 to the 3rd, p to the 6th, q to the 12th. Negative 1 to the 6th power is just 1, p to the 6th, q to the 12th. Now, this problem is asking me if I can take and add these terms. In other words, are they like terms? Well, like terms state that I can have different coefficients out in front, but in order to add these, I must have matching variables, which I do, and matching exponents, which I do. And if that's the case, I keep all the variables the same and add the numbers or the coefficients out in front. So that's 126, p to the 6th, q to the 12th. These are going to be very important concepts to know, and some of the things that are really going to carry forward through every level of mathematics that you do from here on out. Let's go to the next problem. I've got unwritten power of 1, another unwritten power of 1. We're going to take and multiply powers now. So that's 2 to the 4th, a to the 8th, b to the 12th, minus 3 squared, a to the 8th, b to the 12th. 2 to the 4th is 16, a to the 8th, b to the 12th, minus 3 squared is 9, a to the 8th, b to the 12th. And this is a very similar example as the last one. We notice that we have matching variables and exponents. Therefore, we subtract the coefficients out in front. So 16 minus 9 is 7, and we keep the variables the same. Last example, this is a little bit different because we don't have numbers across the board in our exponents. We have x raised to the n plus 1 raised to the 3rd. So this is a base with a power raised to a power. We need to multiply powers. So this is x to the 3 times n plus 1. And this term is once again x to the 4 times n power. Distributing the 3 through, I get x to the 3n plus 3 times x to the 4n. Now we're asked to multiply two terms with the same base. When asked to do that, we keep the base the same and we take and add the powers. Notice when I add these powers, I add like terms, so the 3n and the 4n are like terms, so that's 7n plus 3 power. That's all we've got in this lesson.